book. Successfully added a stream marker. Perfect. All right, so let's get going here on a final project. Building a multi-threaded web server. It's been a long journey, but we've reached the end of the book. In this chapter, we'll build one more project together to demonstrate some of the concepts we covered in the final chapters, as well as recap some earlier lessons. For our final project, we'll make a web server that says hello and looks like figure 20-1 in a web browser. Here's the plan to build a web server. 1, learn a bit about TCP and HTTP. Listen for TCP connections on a socket. Parse a small number of HTTP requests. Create a proper HTTP response. Improve the throughput of our server with a thread pool. But before we get started, we should mention one detail. The method we will use won't be the best way to build a web server with Rust. A number of production-ready crates are available on Crates.io that provide more complete web server and thread pool implementations than what we'll build. However, our intention in this chapter is to help you learn, not to take the easy route. Because Rust is a systems programming language, we can choose the level abstraction we want to work with and can go a lower level than is possible or practical in other languages. We'll write the basic HTTP server and thread pool manually so you can learn the general ideas and techniques behind the crates you might use in the future. Let's get started. Building a single-threaded web server. We'll start by getting a single-threaded web server working. Before we begin, let's look at a quick overview of the protocols involved in building web servers. The details of these protocols are beyond the scope of this book, but a brief overview will give you the information you need. 2 main protocols involved in web servers are the Hypertext Transfer Protocol, HTTP, and the Transmission Control Protocol, TCP. Both protocols are request-response protocols, meaning a client initiates requests and a server listens to the requests and provides a response to this client. The contents of those requests and responses are defined by the protocols. TCP is the lowest level protocol that describes the details of how information gets from one server to another, but doesn't specify what that information is. HTTP builds on top of TCP by defining the contents of the requests and responses. It's technically possible to use HTTP with other protocols, but in a vast majority of cases, HTTP sends its data over TCP. We'll work with the raw bytes of TCP and HTTP requests and responses. So if we're going to be working with the raw ones, what is nice about TCP is that it's guaranteed to arrive at the destination because of what's being sent in the headers, and it's saying like, hey, here is the number of bytes that I'm sending, here's like the first and the end transmissions, let's go. And if it doesn't receive it, the receiver will send a response saying, well, I missed a whole bunch, can you please resend? Listening to the TCP connection. Our web server needs to listen to a TCP connection, so that's the first part we'll work on. The standard library offers a standard net module that lets us do this. Let's make a new project in the usual fashion. So cargo new hello. So not exactly sure I want to call my web server hello. I think I'll do cargo new basic web server. And we'll open up code here, just for good measure. Now enter the code in listing 20-1 in source main rs to start. This code will listen at the address 127.0.0.1, port 7878 for incoming TCP streams. When it gets an incoming stream, it will print connection established. So let's take a look here. I use standard net TCP listener, function main listener equals TCP listener bind to Interesting. So it's a stir that we pass in. So 127.0.0.1. We want to. Interesting also that we're doing 127.0.0.1 and not 0.0.0.0. Which would be a little bit easier to sort of like export out to other systems, but that's besides the point. Then we unwrap that, okay. For stream in listener.incoming, let stream equals stream.unwrap, and then print line connection established. Interesting, okay, so we're going to use the iterator called incoming on the listener that came from TCP Listener. Then we unwrap that so it's a result, and then we'll actually have something with the stream that we can use for responses probably. Okay, so standard net TCP Listener, first thing we're bringing in. And we're doing this in main. Standard net TCP Listener. Once we have that, let listener equals, so TCP Listener bind. Okay. So so our listener equals the TCP Listener dot the, oh, now the double, there we go. Bind, so then the address, I'm actually thinking about doing this, so it's going to be let address equals, we can do localhost right now, so 127.0.0.1, and we're also having to give it the port number, so I'm just going to give it the port number of 3000, because I've been using 3000 for everything recently, so I will continue to use that here. So we'll give it the address. Now we also need to unwrap this because it gives us a result back. So that gives us the listener. Now we want to iterate through the listener using the incoming iterator, and then we can unwrap the stream. So for stream in listener dot incoming. Okay, so then the next thing is we want to shadow stream and get the result from it. So let stream equals stream dot unwrap. And at this point in time, we're not really using stream here. It looks like we're just going to print this line. So I can underline this to make it not complain about that. And we're going to print line web server running on, and I can just put in address. All right, so I'm curious what happens if I attempt to run this now. So let's try that. Cargo run. Okay, well, I mean, it seems like it's running. It's sitting there listening forever. I wonder if I go, do I have, I don't have a Chrome. All right, that might be something I install later. I usually do a lot of my web development on Chrome, and for some reason, I guess I haven't been doing web. I've reinstalled the operating system since I've last done web development on this system. So let's go to localhost :1000. Connection was reset, but we got this web server is running on. So by attempting to like navigate to it and use it, that's what we were able to get. Perfect. Let's continue through here. Using TCP Listener, we can listen for TCP connections at the address 127.0.0.1.78.78. In the address, the section before the colon is an IP address representing your computer. This is the same on every computer and doesn't represent the author's computer specifically. And 7878 is the port. We've chosen this port for two reasons. HTTP is normally accepted on this port, and 7878 is Rust typed on a telephone. Okay, I haven't actually looked at telephone numbers. That's great. The bind function scenario works like the new function in that it will return a new TCP listener instance. The reason the function is called bind is that in networking, connecting to a port to listen to is known as binding to a port. The bind function returns a result, which indicates that binding might fail. For example, connecting to port 80 requires administrator privileges. Non-administrators can listen only on ports higher than 1024. So if we try to connect to port 80 without being an administrator, binding wouldn't work. As another example, binding wouldn't work if we ran two instances of a program and so had two programs listening on the same port. Because we're writing a basic server just for learning purposes, we won't worry about handling these kinds of errors. Instead, we use unwrap to stop the program if errors happen. The incoming method on TCP Listener returns an iterator that gives us a sequence of streams. More specifically, streams of type TCP stream. A single stream represents an open connection between the client and the server. A connection is the name for the full request and response process in which a client connects to the server. The server generates a response, and the server closes the connection. As such, TCP stream will read from itself to see what the client sent, and then allow us to write a response to the stream. Overall, this for loop will process each connection in return and produce a series of streams for us to handle. I wonder, are there any methods that we see off of this underscore stream? If I take you off again, if I go stream dot interesting. What if I do stream.write? Oh, it takes a buffer. I don't have a buffer right now. Okay, I'm not going to worry about it too much. But I bet we're going to do something with stream, and that's how it's going to work. Let's try running this code. Invoke cargo run in the terminal, and then load 127.0.0.1 port 7878 in a web browser. The browser should show an error message like connection reset, because the server isn't currently sending back any data. But when you look at your terminal, you should see several messages that were printed when the browser connected to the server. So we got that. Sometimes you'll see multiple messages printed for one browser request. The reason might be that the browser is making a request for the page as well as a request for other resources, like the favicon.icon icon that appears in a browser tab. It could also be that the browser is trying to connect to the server multiple times because the server isn't responding with any data. When stream goes out of scope and is dropped at the end of the loop, the connection is closed as part of the drop implementation. Browsers sometimes deal with closed connections by retrying because the problem might be temporary. The important factor is that we've successfully gotten a handle to a TCP connection. Remember to stop the program by pressing Ctrl-C when you're done. When you're done running a particular version of the code, then restart cargo run after you made each set of code changes to make sure you're running the newest code. That is a very common problem with a lot of web development server things. The number of times that I've like, why won't this change work? And then it's just because I made 3 or 4 changes and I haven't actually restarted the server. That's a thing. Reading the request. Let's implement the functionality to read the request from the browser. To separate the concerns of first getting a connection and then taking some action with the connection, we'll start a new function for processing connections. In this new handle connection function, we'll read data from the TCP stream and print it so we can see the data being sent from the browser. Change the code to look like listing 22. So it looks like we're going to need, so we already have a TCP listener, but we're going to add in the standard IO prelude and the standard net TCP stream. So this line stays the same, these stay the same. We're then going to run a function called handle connection, pass it the stream. So it looks like we're also going to be giving ownership of the stream to handle connection. Handle connection takes, interesting, mutable stream where we're not saying it's mutable here, which is type TCP stream, so that's why we need that there. Let mute buffer equals 0 and 512. Okay, interesting. And so initializing a raw buffer, and then stream.read mutable buffer. So this is going to read into the buffer, I think, right? And then we can print the buffer and convert it into UTF-8. All right, let's do it. So we're going to need the, you know, let's just try coding this and see if we can get the error message to tell us exactly what to put in. I keep on like wanting to see that because I love how Rust has the helpful error messages. All right, so we've already got the listener, we've already got all these things, but now we need this function called handle connection that we can pass the stream to. So instead of this, we'll say handle connection we'll pass the stream, but we'll also give ownership to it. So we have function handle connection. This takes a stream, which is type, it's going to be type TCP stream, which of course doesn't exist yet. So we need to actually pull that in. So that's where use standard net TCP stream. This one probably wouldn't have given us the error because it would have been like, hey, you're just trying to use a type that doesn't exist yet. All right, so unused variable stream, that's fine. We also aren't returning anything here, so we need to create this buffer. So let mute buffer equals, and it looks like we're starting with a 0, and we're going to what? 512. Okay, that looks right. Then we're going to stream read, pass it in that a mutable reference to that buffer, and unwrap it. So stream dot we want to read. We're going to pass it the mutable buffer, so mutable reference to the buffer. Of course, this returns a result, and so we're going to naively unwrap it because I'm sure it's perfect and won't fail. And once we've got that, then we're going to print line what this request is, string from. So looks like then we have to convert the buffer into a string, but there is a native method off string for that. So then we can do print line the incoming stream. All right, so it's going to be string from. Now inside of here, is it string from? No, it's string from, so it's not just from. UTF-8 lossy. Okay, so we're going to take it from UTF-8 lossy. Let's also close this down to give us more room. And so inside of here, now we're going to give access to a reference to the buffer because we don't want to give ownership to the buffer right now. Reference to the buffer, and we need to pass it everything inside. So was that 3? No, that's 2. And semicolon. All right, so this read, no method name read for found for type standard. So I believe that this is where the prelude comes in. So let's see if I can run this and if I can get that error message. So no method named read for type. The following trait is implemented but not in scope. Perhaps add a use for it. So standard IO read. So it doesn't tell me to use the prelude. It just tells me to use, well, to use use. So use standard, say IO. It does. So it says IO prelude star. So if I do that, that should make this go away. Now we have stream here. Cannot borrow immutably argument stream as mutable. Oh, I think we brought this in as mute in the book. All right, let's try it. Let's try it again. Web server seems to be up and running. Let's hit it. All right, so the incoming stream, which I think I misspelled. So get HTTP1, host is, the address that the browser's coming in on. User agent, so Mozilla. Make this a little bit larger. X11, Ubuntu, Linux. So everything about my system. So these are all the things that web servers can actually get about your computer. Just by receiving the request. Accepting text HTML application XHTML plus XML. So basically what like the data type that the browser expecting, HTML essentially. Accept language, accept encoding so it can gzip. Connection is keep alive, and upgrade insecure requests is nice. We bring standard IO prelude into scope to get access to certain traits that let us read from and write to the stream. In the for loop in the main function, instead of printing a message that says we made a connection, we now call the new handle connection function and pass the stream to it. In the handle connection function, we made the stream parameter mutable. The reason is that the TCP stream instance keeps track of what data it returns to us internally. It might read more data than we asked for and save that data for the next time we ask for data. It therefore needs to be mute because its internal state might change. Usually we think of reading as not needing mutation, but in this case, we need the mute keyword. Next, we need to actually read data from the stream. We do this in 2 steps. First, we declare a buffer on the stack to hold the data that is read in. We've made the buffer 512 bytes in size, which is big enough to hold the data of a basic request and sufficient for our purposes in this chapter. If we want to handle requests of an arbitrary size, buffer management would need to be more complicated. We'll keep it simple for now. We pass the buffer to stream.read, which will read bytes from the TCP stream and put them in a buffer. That kind of makes me wonder, what happens if I have like way too small in here? Will I get a buffer overflow error? And it will basically return a result error, which will then panic right here? Or will it just cut off and not display everything? Let's try 64. That should hopefully not be enough. Okay, so our server's running. Let's hit it. Ah, interesting. to the incoming stream. We get this information. Just right in the middle, it gets cut off. So it won't give us an error. It will. It'll be just happy to just not print everything. So we had 512, 1024. Next one in the binary series. So let's make sure there's no like other data here for us to care about. No, there isn't. But I could keep it as that just in case. There's no real problem with using a little bit of extra memory. Right now, at least. Next, we need to actually read. Oh, we did that. Second, we convert the bytes in a buffer to a string and print that string. The string from UTF-8 lossy function takes a vector slice and produces a string from it. The lossy part of the name indicates the behavior of this function when it sees an invalid UTF-8 sequence. It will replace the invalid UTF sequence with a question mark. The U plus FFFD replacement character. You might see replacement characters for characters in a buffer that aren't filled by the request data. Let's try this code. Start the program and make a request in a web server again. Note that we'll still get an error page in a browser, but our program's output in a terminal will now look similar to this. They're using Windows NT. I think like everything has been Windows NT ever since then. So they might be working on like, yeah, Windows NT 10 or something like that, Windows 10. Depending on your browser, you might get slightly different output. Now that we're printing the request data, we can see why we get multiple connections from one browser. Request by looking at the path after request get. If the repeated connections are all requesting slash, we know the browser is trying to fetch slash repeatedly because it's not getting a response from our program. Let's break down this request data to understand what the browser is asking of our program. A closer look at an HTTP request. HTTP is a text-based protocol, and a request takes this format. So method request URI, HTTP version CLRF, headers CRLF. This is the CRLF is the new line thing. So carriage return line, line feed line. I forget the LF. But it's basically Windows and Mac friendly. And then message body. The first line is the request line that holds information about what the client is requesting. The first part of the request line indicates the method being used, such as get or post, which describes how the client is making this request. Our client used a get request. The next part of this request line is slash, which indicates the uniform resource identifier, URI, the client is requesting. A URI is almost, but not quite, the same as a uniform resource locator, a URL. The difference between URIs and URLs isn't important for our purpose in this chapter, but the HTTP spec uses the term URI. We can just mentally substitute URL for URI here. So since we're not really getting into it, the big difference here is that URL is something that you like type into the bar, and URI is like just a little bit more inclusive into alternate protocols. So if you have like WebSockets, it would be WS, or secure WebSockets WSS : //. So basically, it just is better for more options. Here we go. The last part is the HTTP version the client uses. And then the request line ends in a CLRF sequence. CLRF stands for carriage return line feed and line feed, which are terms from the typewriter days. The CRLF sequence can also be written as \r, \n, where \r is a carriage return and \n is a line feed. The CRLF sequence separates the request line from the rest of the request data. Note that when the CRLF is printed, we see a new line start rather than \r, \n. Looking at the request line data we received from running our program so far, we see that get is the method, slash is the request URI, and HTTP 1.1 is the. So let's go and double check that in here. So we see the get to slash. HTTP. And obviously the host and everything else. So perfect. Let's see. Looking, we got that. After the request line, the remaining lines starting from host onward are headers. Get requests have no body. Try making a request from a different browser or asking for a different address, such as 127.001.7878 test to see how the request data changes. Now that we know what the browser is asking for, let's send back some data. So one thing we can try is we can also try curl. Curl, it is a get by default. So we can just do to local host colon 1000. Okay, so here's the one from curl. Notice that there's so many, there is less data coming from it. So it's still a get to slash, but the user agent is curl. There's no headers, and it's still to localhost. Also, something that's interesting is that when I put in, I did one localhost too, so it's fine. Now that we know the browser is asking for, let's send back some data. Writing a response. Now we'll implement sending data in response to a client request. Responses have the following format: HTTP version, status code, reason phrase, CRLF, headers, CRLF, message body. The first line is a status line that contains the HTTP version used in the response, a numeric status code that summarizes the result of the request, and a reason phrase that provides a text description of the status code. After the CRLF sequence are any headers, another CRLF for sequence, and the body of the response. Here is an example response that uses HTTP version 1.1, has a status code of 200, an OK reason phrase, no headers, and no body. So HTTP 1.1, 200, OK, and then our CRLF. Notice that they just do one right here. That's just because, I mean, it's sort of like comma separated values. Instead of commas, we're just doing new lines. The status code 200 is the standard success response. The text is a tiny successful HTTP response. Let's write this to the stream as our response to a successful request. From the handle connection function, remove the print line that was printing the request data and replace it with the code and listing 20-3. Okay, so from the handle connection function, remove the print line that was printing the requested data and replace it with the code and listing 20.3. All right, so in handle connection, everything is the same here. We're getting our buffer, which is the same, stream read. Let response be, and then we're just going to manually create this entire string. Looks like we're sending that OK string. And then stream write response as bytes. So response as bytes. Unwrap that, and then stream.flush to actually make sure it gets sent out. All right, so looks like all we need to do now is just create a response string. That. Okay, so let response equals, it's really just going to be this string here, right? So HTTP, is it all capitalized? HTTP /1.1 space, and then we can have the status code and then the string. So we're going to have 200 and okay, and then we're going to have two sets of /r/n because r/n. Now we're in a header section and we don't care about this, so /r/n, and now we're in the body, but there is no body, so then that's the end of this. Now we want to stream.write and then this, so stream.write. It's going to be the buffer, so it's going to be response dot as bytes. Seeing that it doesn't have that, and then obviously it's passing back a result. We're going to unwrap that. Attempted to take value of method as bytes on type string slice. Maybe a all right, so it needed a function. Okay, so let's try that. Okay, so we have that running here. If we switch over to our curl here and we run this, we get nothing back, but we no longer get this empty reply from server. Now we still get the incoming stream once. Let's go try this with the web browser. Now we don't get the error anymore. And interesting, this happened twice. Okay, so let's take a look at what we've got. The first new line defines the response variable that holds the success. Oh wait, is it going to be the same thing? Get right. Okay, so take a look. It happened twice for a very for an interesting thing. It did a get to slash. As soon as it successfully got to slash, it did a get to /favicon.ico. So notice this tiny little icon right here on the top. We have them for, like, you know, Twitch has the little purple talking guy thingy. GitHub has the Octocat, and apparently this book has a little book icon. Those are the favicons. So if we had a file and it could do a get to that, and we can upload and send the data to the browser, and it would display right here for us. The first new line defines the response variable that holds the success message's data. Then we call asBytes on a response to convert the string data to bytes. The write method on stream takes a slice U8 and sends those, so a vector reference to a vector of U8s, and sends those bytes directly down the connection. Because the write operation could fail, we use unwrap on any error result before again, as before. Again, in a real application, you would add error handling here. Finally, flush will wait and prevent the program from continuing until all the bytes are written to the connection. TCP stream contains an internal buffer to minimize calls to the underlying operating system. With these changes, let's run our code and make a request. We're no longer printing any data to the terminal. We won't see any output other than the output from cargo. When you load, oh, I noticed that they removed the print and we didn't. With these changes, let's run our code and make a request. We're no longer printing any data to the terminal, so you won't see any output other than the output from cargo. When you load 127.0.0.1 on your web browser, you should get a blank page instead of an error. You've just hand-coded an HTTP request and response. Returning real HTML. Let's implement the functionality for returning more than a blank page. Create a new file, hello.html, in the root of your project directory, not in the source directory. You can input any HTML you want. Listing 20-4 shows one possibility. So, that actually, Okay, so here I'm gonna touch index.html because the default file that gets sent back according to the HTTP spec should be index.html, not some arbitrary other file. Although like that is a holdover from like, you know, a long time ago. It could be changed, but for right now, like stay with the traditional. Which means that in code we can update this. So are you gonna call? I'm hoping to like get the there we go. Oh, it didn't give me the doc type. Okay. The doc type. Oh, I always have it do it for me automatically, so I always forget exactly what it is. Just bang doc type HTML, all uppercase. All right, so we have this in our title. It's gonna be hello from a Rust server. And then here, let's give ourselves an h1 tag of hello from Rust. Now, assume that we're going to be, when we get this stream, if it's on slash, we can then maybe have another function, call that function to like handle that slash request. It will grab the file, so load it into memory, and then convert it to bytes and send it off. All right, so we've did this. This is a minimal HTML5 document with a heading and some text. To return this from the server when a request is received, we'll modify handle connection as shown in listing 20-5 to read the HTML file, add it to the response as a body, and send it. Okay, so not a new function, but we'll do okay. Contents. So contents fs read to string hello.html.unwrap. Right, because contents will be just the raw bytes, I think now. Because now we can just have. Interesting. So response. This is all just like the status message and everything else, and then the contents. If I remember correctly, in HTTP 2, this OK is not required. So that will be interesting, like writing those servers. Stream write, response. So that will be the exact same. So we're just changing the format here. So let's bring in standard FS, and we'll do all the things. So use standard FS. And of course, we're not using it yet. So we have stream read, buffer, response, contents. So in here, so I'm going to call this index HTML equals, so this is going to be not a for in loop. So fs dot, I think it's double colon, read to string. So that's the problem. Read to string. So the path is going to be, I believe, just slash index.html. Oh, interesting. So it's not slash. It's just index.html. And then we obviously need to unwrap this because it is returning a result. So that gives us the index. The response can now be a format. And this is fine. Did I see that? Yeah, right after that, then they have the actual body here. So this here, and this is going to be our index HTML. Close it off. So now we can just send a response as normal, and we should get that. Let's try running this code. Cargo run. Okay, running our server. And here we got hello from Rust. We can inspect the code here, and specifically I want to inspect the network. So we can see got our status, code 200, method get, remote address here. So, oh, these are just the status codes. And these are what we requested. There's not really anything crazy in here. It's just pretty simple stuff, but pretty awesome at the same time. Let's go back to the book. Oh, we've added a line at the top to bring the standard libraries file into scope. The code for opening that file and reading the content should look familiar. We used it in chapter 12 when we read the contents of a file for our IO project listing 12.4. Next, we use format to add the file's contents as the body of the success response. Run this code with cargo run and load 127.0.0.1 port 7878 in your browser. You should see your HTML rendered. Currently, we're ignoring the request data in buffer and just sending back the contents of the HTML file unconditionally. That means if you try requesting 127.0.0.1 port 7878 something else in your browser, you'll still get back the same HTML response. Our server is very limited and is not what most web servers do. We want to customize our responses depending on the request and only send back the HTML file for a well-formed request to slash. Let's see, this section is decently long. So what I think I'm going to do is I'm going to leave this for next time. So tomorrow morning, I'll be continuing to work on starting with validating the request selectively and responding. Let's go ahead and add in a marker here. So /marker ending today. All right.